Thank you so much, everyone, for coming here. I'm delighted to introduce our Hanover speakers today. Dr. Julie Rieland, she got her undergraduate degree from University of Michigan in material science. Then she also started doing her PhD in University of Michigan, but in Department of Macromolecular Science and Engineering under Professor Brian Love. And she's currently working as in natural resource. Is it?
It's a
what is NRC standard?
National Research Council.
Okay, sorry, National Research Council in as a postdoctoral fellow in NIST. Please join me to welcome Julie. Thank you.
So, yeah, thank you for coming. So, I'm hoping to take you on a journey to interconnect some of the research that I've done over the last several years, connecting how an interdisciplinary approach linking social science research and also bench science research of a lot of different varieties has really kind of shaped my perspective on plastic pollution and presenting kind of a vision of where I think we should kind of collectively be going as people trying to fix the problem. I might be tied here. Oh dear.
Yes, it's okay. I think you should probably put the mouse there.
Oh, I guess that's supposed to be attached.
Yes. Or just yep.
Okay, let's try them. Okay. Yeah, thank you. So, Mojgan nicely introduced some of the high-level things. But what's hidden under this is over the last 10 years of research, I've actually worked in a wide range of fields, ranging from polymer synthesis in a chemistry lab to mechanical testing, breaking things, all the way to doing social science field work with farmers down in Kansas. And so I'm hoping to connect these all into a narrative and hopefully talk about 2, if not 3 of these topics, depending on how much I get chatty. And then in the process of pulling these slides together, I actually thought of a better title because it was about 6 months ago that I submitted that title. And so today what I'm going to be presenting on is systems thinking as a process for pathfinding in complex problems. So a great place to start is, what is a system? And at the very simplest core, it's stuff wrapped around a boundary. And this is a constructed thing, but they do have very real impacts. We have ecosystems, political systems, economic systems, and the boundary is somewhat arbitrarily drawn, but often there's a logical reason why we've put those boundaries there and articulate that. And within a system, these things interact with each other and they create processes and nodes and stakeholders, and they interact, developing a behavior that is kind of expected of that system. And so these systems can be self-contained. If you think like a car engine, that's a system, a mechanical system, or they can be very porous and inputs can come in and out. And so when we start thinking about things in systems, we can start thinking about higher level processes and how they interact with each other. And so some of the most important processes that happen in systems are feedback loops. And so we can have positive feedback loops where things beget more things. Think car traffic. We have traffic, we add more lanes, more people decide to drive, we get traffic again. And it just keeps reproducing into this bigger and bigger process. We also have negative feedback loops. And so this is something like if you have a detrimental event, there's less food in the ecosystem, there's less food, that creatures have less babies, you have less adults, you have less babies, and your population starts to shrink. And so you have these different kind of behaviors that are very consistent across systems. They just look different, but it's the same kind of processes that are underlying. And those, you can have subsystems that grow into these large interconnected systems. And when you bring that into a real world where you're trying to map systems, it can get very complex. And so this is this author's take on kind of what is happening as far as our movement towards a circular economy of plastics. And let's see, to kind of bring this into a more understandable level, because those diagrams are big and scary, I wanted to present 2 short narratives that can help us kind of think about how this looks like on a day-to-day basis as a researcher. And so first I want to start with kind of that old nursery rhyme of the little old lady who swallowed the fly. And I promise this goes somewhere interesting. So the story of the little old lady who swallowed the fly is that there was a crazy old lady who swallowed a fly. And for some reason she thought, well, the best way to fix that would be to swallow a spider to get the fly, and then a bird, and then a cat, and so on until she dies. And this sounds like a crazy person, but we actually do this all the time as a species. For instance, back in the day, we brought something in, it got invasive. How do you manage it? You bring its natural predator, and then it doesn't eat the species you wanted it to eat. It eats all of your other species. We do this in medicine to an extent. It's a much more complicated story, but grandma goes on blood thinners, and now she's nauseous, and now she's not eating well, so we need diet stimulants. And there's just these positive feedback loops that kind of viciously replicate. And then as scientists, we also do this because we don't look up high enough to see, is what we're doing actually going to fix the problem? Like some of our most pernicious PFASs are polyfluoroalkyl substances were created because we thought they would be healthier and more sustainable to us. So we created them, we didn't test them, we put them out there at vast quantities, and now it's persistent in our water, our soils, our bodies. It's a problem, and we need to be thinking at these systems levels and not just at what's in front of us to try and fix it. So I'm going to come to this one other narrative that I really enjoy, which is how do we build a better clothes dryer? And this is a model for how can we think about systems more effectively to better wield leverage points to change things. So this is a question that was really posed at like a washing machine company. And they said, well, we're getting pressure. We need to be more energy efficient. We want those stars. The customers demand it. So how do we go about building a better clothes dryer? And the logical thing to start with is, what do you want the clothes dryer to do? You want it to dry your clothes. You want to use less energy. We can throw some extra things in. We want it to not damage the clothes. And we'd like for it to be quiet. That would be great. And if you're cheeky, you can say, why don't you just hang dry your clothes? But let's say we also want to be faster than hang drying and also space efficient, because that takes up a lot of space. And I live in a small apartment just outside of DC, and that's out of premium. So what we could do is we can put on our thinking cap and pull out our scientific toolbox, and we can start running through these ideas of how might we problem solve this. And if you brute force it, we could add more heat, but that doesn't, you get faster, but it doesn't fix the energy problem. We could try and put more airflow through. It fixes some things, but doesn't fix our energy problem. If you put your chemistry glasses on, you could start going nuts and say, we're going to use the azeotropic effect. We're going to add extra solvents that's going to reduce the vapor pressure of the water. We can now get the water out of there with less energy. We've solved it. No, less energy, less damage, faster. But now we have greenhouse gases that we have to worry with. There's a whole new supply chain. And is this product, if it were viable and checks all the boxes, is it going to be at a price point that people will actually buy it? So you kind of come back to the drawing board and say, well, at a certain point, you can't beat thermodynamics. The washer is doing about as well as we can. And so then now we think of it at a system scale, and you say, well, my system is the wet clothes and the dryer. What more can we do if we're at the limit of thermodynamics? Really, the trick is you can expand your system out. There's no reason that your system is constrained to that area. And you say, well, you know what's a lot easier and cheaper and doable, and you get that Energy Star rating, is you make a washing machine that makes your clothes less wet on the other side, and the washer and the dryer doesn't have to work so hard. And so this is an idea of how we can kind of start thinking about systems as tools that we can expand our point of view. and introduce this into how we're going to leverage these systems. So keeping these kinds of ideas in mind, I want to talk about some of the research that I've been doing during my postdoc. And so one part of the project that I've been doing is going out to talk to farmers about their plastic usage down in Kansas. And so what I set out to do was go down to Kansas, give a survey to farmers, and try and figure out what kinds of plastics they're using, how much of those plastics they're using, do they have recycling, what's being recycled, how much is being recycled, how do they feel about their plastic usage? Like, are they happy with what they're using, how they're using it, how they're disposing of it? And I can say we answered those questions. And so by getting 73 mostly complete surveys, accounting for about 115 square miles of farmland, we identified that about 70,000 kilograms of plastic is being generated and disposed of on these farms. But what we hadn't factored into our calculation when we went down there is this terrifying fact that about 56% of that is being open burned on farms, like pile it into a pit, add the gasoline, light it on fire. That's a lot. And 83% of the people that I was talking to said they burned some, if not all, of their plastic waste on the farm. And this is in the gray area of illegal, not illegal, but this is a widespread habit. This is how they've done it for centuries. This is what makes sense to them and is most accessible as a waste management problem. And if you square these numbers up, we have 83% that are burning, 25% that are landfilling, and only 51% that are carting their stuff out to landfills. And like, I would talk to these farmers, and I mean, some of them were really gung-ho and it's like, yeah, we burn it. And some of them were like, we burn it. We wish we had a better way to do with these things. And it's a lot of stuff. So like, this is those tick marks, those are metric tons. And so that's about 44 tons of plastic being burned just on the 70 farms that I talked to. And we have hundreds of farms just in Kansas alone. And of course, the different municipal areas have different laws regarding how legal and how enforced that is. But this is a sizable problem. I don't remember where this goes next. But it's not something that I was expecting to see, and so I didn't ask questions about it. I didn't ask, why are you burning all your plastic on the farms, and how can we stop you from doing that? But when you submit papers, they're like, your reviewers are going to come after you, and they're going to say, why are they doing that? Tell us, and then they won't let you publish until you answer their question. And so we dug deeper into the data, and we did start to find some underlying causes that we speculate on why they were doing this. And so our first piece of evidence that we found that was kind of interesting was that there was a statistically significant negative correlation between people recycling and people not going to the landfill. And so we start to see this interesting, like, so the people who are recycling might be more likely to also be burning plastic. That's like a cognitive dissonance, right? They're having some of the better behavior and some of the worst behavior all at the same time. So without knowing exactly the facts about why these behaviors are replicating in the system, we can speculate that very commonly out in these backwoods areas, there's no curbside recycling, there's no curbside trash. You are collecting all of your waste that you produce in your house, in your farm, and you're carting that to the landfill, and they're charging you by the ton. So it's costing you money to recycle, it's costing you money to landfill. It's taking you an hour round trip to go do this. You're not doing it twice. You say, I really want to recycle as much as I can. I'm going to do the trip for the recycling, and I'm not going to do any more work on this. Everything else is getting burned. And so we start to see that the incentive structure for how these people have to interact with the system that they have access to is all out of whack. And we can start to think it's not a bad behavior problem, it's an access problem. And kind of reinforcing that, we looked at who are the recyclers and who are the, who is doing these activities. And what we found was that our recycling farms are smaller farms. Like this is a log scale. So these green triangles who are our recyclers, and this is their amount of plastic waste that they're generating on a year. Even if we have 25% of the population participating in recycling, it's still not representative of a lot of the overall material that we produce, because log scale, our recyclers are down here. And we have a lot of large farms out there. And the thing about recycling on a farm is it's a lot of hassle. So they have to go retrieve it from the field, they have to clean it, they have to cart it out to the recycler, and they probably have to pay a fee on the other end. And going back to what we had found before, this was also representative in our behavioral data when we asked people what they would be willing to do to participate in recycling. And so we already knew off the bat that they were going to be resistant to transportation and paying fees. But it's a scaling issue now too, because if your farm's producing 5,000 kilograms of this one material, that's a lot of labor. If you don't have mechanization, it's just not tractable as a problem. So you might as well put it into the big dumpster. And we're hoping that those larger farms are the ones landfilling and not burning. So we start to see these kind of replications of systems and feedback loops and what it takes to actually get things done at a scalable size. So as a side effect of doing this research, I was like, wow, that's crazy. So I went to see, like, what does the literature say about other farm surveys? Like when people go out into the farming community and talk to people, what is going on here? And so my numbers are up here at the top, and this is participation rates, not like mass rates. And we see that like we're in line for burning with, like, you know, Iran and rural China, at least in this Kansas population. But if you go along, like, it's infrastructural management at a municipal level. We have a couple different kind of degrees of what's going on with waste. So if 51% of my farmers were taking their stuff to landfill, that looks different than no landfill in Korea, because they're mostly doing incineration. It's just smaller countries, high populations, you have different ways of dealing with trash. But then we go to Ghana and no waste management, and we can speculate that at least at the time of this survey, they probably didn't have community level waste management in the first place. So burning and burying and dumping are kind of what you get. But then if we go to recycling, we're actually doing middle of the pack. We're about in line with Canada, and Canada is doing massive investments in their farm recycling capacity. But like outside of kind of developed cores and the EU and Asia, I mean, we're doing pretty good. This one study out of Tennessee from a few years back, they didn't have access to recycling at all. So now let's expand even further out of the system view. Past agriculture, we're going to all plastics generated in the whole world. And we can start building these structures that look at what are the mass flows of plastics, where are they going, do they start, where do they end up? And what you see in this diagram is that we have a very linear waste processing system, very much that take, make, waste paradigm, where we really want to close that circular economy and really accentuate this green recovery loop and minimize the waste, linear waste, and particularly our environmental losses. And this is where that open burning and like dumping take place. And so this becomes an everyone problem. And the current stats is that we're exponentially increasing how much plastic we're making every year. And this problem is only expected to grow. So we're at this kind of double bind where there's areas that don't have infrastructure. And it just seems such an intractable problem. And it's really hard to know where to start, what to do, what will actually cause impact, and how do we do this without releasing more invasive snails that are going to eat all of your endemic population. And really, this is a problem everywhere, from the slums of India to New York City to the middle of the Pacific Ocean. It's a huge issue, and we're really just adding gasoline to the fire. So it kind of pulls you back to this systems diagram, which is still incredibly complicated because this only shows kind of one dimension that you can expand out into pretty much all of the social systems that we have kind of constructed around us. And I call this my systems tesseract, because it's just 5-dimensional chess of where do we poke the system to try and get change. So something I've been thinking about in the process of really pulling these sides together and trying to think about how we can use systems to really start tackling this problem and to give us a language to talk about the problem, where we can start to make tractable pose, has come back to ecological succession and these models that seem quite robust and gives us at least a landscape of, we can look at a place and say, okay, this is where you're at. We think you should be going here. How do we get from here to here? And I think that there's a very logical flow of our infrastructural capacity for waste management to introduce this idea of an ecological succession model for plastic waste. And it works even at our primary and secondary level succession models where, well, if you think of the Roman middens, and they had their dumps back in the day. We've had dumps and garbage disposal for the whole history of human culture. So you have your primary succession model. Eventually, we started to build more technologically advanced systems to handle our waste and trying to, if not decentralize the pollution, actually manage it long term. But we also have this secondary pollution succession model where if we have a natural disaster, if we have political unrest, if we have economic collapse, your infrastructural waste management system is collapsing along with it. And so we have these models of destruction and cyclical stage progression in our municipal communities as well. And we can start to kind of think about, like, where might these stages be if we go from kind of community scale, put your waste in a pile and burn it. That, I mean, at least makes it go away and it's not making you sick and pulling rats in. It's a method of care when that's all you have access to. But then once we have more resources, we can maybe start to build something like a sanitary landfill that at least pushes the water pollution off for 60 or 70 years until you have to think about it again. And then into, like, going back to our model, we can start to think, well, where are these different countries on my hypothetical landscape of a succession model? Where you have something like EU countries that are really racing to the finish line on getting things recycled. But I think that we hit a wall because things aren't designed to be recycled, and we don't have the technological capacity to recycle everything, even if we could collect it, separate it, get it to the places where it needed to be. And so we hit that technological wall. And eventually, I think what we really want to do is design plastic insofar as possible out of the equation, because we're using the plastic and it's making microplastics. So you wear a polyester shirt, you wash it, it sheds, it pills. That's microplastics going into the wastewater treatment, out into the environment, back into our farmland. We're never getting those back. You have to buy a new pair of shoes because you have no tread anymore. That's microplastics in the woods. And so we can start to think about these paradigms of what does it take, like our poorest countries, if all they have access to is open burning, what does it take to get them doing something that's a little bit better? And a lot of that's money. And that's a really hard question because money's hard to come by these days. And infrastructure takes years and embedded capital. But if we go from stage 2 to stage 3, kind of like what we're trying to do as a country to try and catch up with some of the really cool stuff that like Europe and Japan are on, we need political will to institute policy, regulation, incentives that get people to cooperate with these new processes that we're trying to embed. And then we hit that wall and we need technological advancement to say, these plastics are recyclable, we have scalable processes that can handle it, and we have a place to put the material on the other side. Because that's also a huge issue, because we can recycle and we can generate more recyclate than we know what to do with, because it's worse quality material and it's more expensive than virgin plastic. So our incentive systems are all out of whack for how we get from place to place. And then in the last stage, finally, we do need to get people to engage with these systems and to get to a place where we're replacing out our materials, maybe going to biodegradable materials, or just restructuring our economic system. So like, you don't need a plastic bag or a new container. You go and get something refilled, or you get it repaired, or you get it traded and swapped and bartered. These are new economic systems that we have to get people to buy into, become used to, figure out how to engage with. So if I haven't talked too long, I'd like to talk about 2 research projects that I have that are kind of pushing us up towards this wall and looking at transitioning us out of stage 4 into a stage 5 kind of economic structure. So starting with this one, because I promised biopolymers. So there's, I think, a lot that we can learn from looking backwards, because plastics only came on the scene around World War II, and they didn't really take off until the 50s and 60s. Like, even just going back to the 1910s, we were seeing glass, metal. Like, we lived a fairly modern lifestyle before plastic. We could do it again. And I mean, there's millennia of ways of living and existing that we can learn from that, I don't know, we could try and learn from. And then kind of you start to see the onslaught of plastic into the 50s to where everything that we interact with today almost has some sort of plastic component, even the electronics of your computer. So the question is, how can we move from this very single-use, disposable, linear system to a more circular system, and hopefully on a more reasonable time scale before we like really make some lasting damage on this planet. And I posit that going back to biomaterials is a really good place to start. And so plastics are polymers and they're synthetic, and most of the plastics that we use are fossil fuel based. So polymers just means it's a very long, wiggly molecule. It gives you flexibility, durability, robustness. You can beat it up and it's going to work. But really, we can access these same kinds of molecular structures using biomaterials, and we can get structures as diverse as tree leaves, tree bark, tree wood, the shells of crustaceans, and the soft, wiggly hydrogels of a lot of plant life. And this is all biomolecules. And these probably look very similar to you. And this is all that it takes chemistry-wise to go from the wood of a tree to the shell of a shrimp. Like, there's a lot of really interesting chemistry and opportunities here if we can just develop the scalable technological processes to take it from a tree to a piece of clothing. And we've been doing that for almost 200 years now. So like, if you go to the store and you see modal, tensile, viscose, rayon, those are all synthetic celluloses. So we've taken cellulose, we've dissolved it, we've extruded it into fibers, and made worse versions of cotton. But it's tractable, it's scalable, we've done it before. Why not replace some of the other things that are shedding microplastics into our environment? And so looking at that, it becomes, again, the separations issue of trees are very complex species. And one of the things that I'm very interested in getting is to get biologists who understand this structure to talk to the engineers and chemists who are thinking about it at this structure and saying, I just want this. How do we get it out of there when this is this? Because the engineers see this and we're like, okay, yeah, we can dissolve that. But you look at a tree and it's like, what am I even looking at? Where is this? And so there's some language barriers that we need to overcome so that we can start to make advancements and think about these separations and what are the processes where we break this down into this, and how can we do that better? Because a lot of what we have now are also polluting processes that are creating greenhouse gases, water pollution, and who knows what other knock-on effects will come from some of our current technological lab-grade experimentation. So one of the mechanisms for this that I've been looking at is ionic liquids, which are highly polar organic solvents that can come in and break those strong polar bonds, the hydrogen bonds that link our cellulose together. And we can actually bring it into solution under fairly mild conditions, and I can dissolve trees. And we dissolve the tree into this, the wood into this ionic liquid solution. And then we add water, we reject those polar molecules into the water, and the molecules stitch back up, and it's now a fiber or a film. We can reshape it and have some degree of properties. And so this is actually, there's some pretty advanced work in the field of ionic liquids, mostly happening out in Europe and some labs out in Finland and the UK. So I figured I would start with a place that asks, how much junk can we shove through this? Like if I take dry fruit without any pre-processing, what happens when I dissolve it into these ionic liquids? And what I found was I could get enough rheological properties where I could stretch and kind of extrude fibers from that coffee fruit, but these were so weak once I dried them and got the solvent out that they'd break before I could do any mechanical testing. And so there's a benchmark. We need to do some pre-processing, so we're not going to get away from that. But the next project that I took was, what is the minimum amount of pre-processing that we could do to these materials to actually get kind of functional properties? And so here you can see actually about 1 meter of my coffee fruit extruded into a fiber. And this one, all I did was treat it with hot ethanol. So something that we can recover the solvent with pretty low energy and exclude all of the junky ionic liquid that's sucked up all of my lignin and sugars and pectins and stuff. And we can make fibers that are as fine as 20 microns. So that's about 5 times as thin as a human hair. And I even was able to run mechanical testing on just this mild ethanol treatment. And what you see here, if these numbers mean anything to you, is that I got an average of about 25 megapascals of strength, which is actually starting to get into a usable level of strength for a material. But kind of, this is my dissertation work, so it kind of ended where it ended, as you'll find out when you get to the end of your PhD. But one of the issues that I found was that we could probably tap higher strength, but we're running into some geometric issues that are once again kind of an issue of spatial conservation. We're running in, once again, victims of the laws of physics, where we're dissolving our material. So it's upwards of 90 to 80% ionic liquid when I extrude it, and we have this nice round, smooth surface. And when you remove 80 to 90 volume% of something, you get volume collapse. And so we have these very high surface area fibers. And that can be good for linking into like a matrix. If you're trying to epoxy embed these, that gives you a lot of surface area to adhere to. But if you're looking at tension, these are crack propagating surfaces. So every one of these kinds of sharp edges that happens when my fibers dry is a point of failure. And so we have a geometry problem of being able to logistically go from a paradigm of where we start with these nice round surfaces that are very strong engineeringly and geometrically to a very weak structure that needs some consideration on how do we access better surface area when we are fighting the laws of physics. And so I actually have time to talk about the other project. So, I wanted to kind of leave some thoughts here. So once we can start to make these biopolymers at scale, there's a question of where should we apply them and where should we focus our energy at designing products out of these biopolymers. And my personal take is that we should be looking at where are they going to be shedding the most. So we use a lot of single-use stuff, and these are all lightweight, low density, escape from the trash can kind of things. So what is the products that are going to most likely escape from our municipal waste management systems, and how can we replace those? And then, so I've been doing a lot of work in the agriculture community and going out to look at agriculture materials and how we can do those better. And there's, of course, the huge amounts of plastic. And a lot of these people, frankly, don't have better things to do with like easy ways to access managed landfill. So it would be really beneficial if they could just leave these in the field and let them biodegrade and have them be much less work on their part and still at least a net zero on physical plastic residue in the environment. But I wanted to encourage you to think about like, where are your domain expertise? Because coming from the polymer science field, a lot of us don't get out of the lab and talk to people. And you only know as far as your vision of like, what are plastics that are an issue? And so thinking like, where are plastics that you see that are escaping our management or just in places that are just completely intractable? And how might these be areas and markets that would be really benefiting from biodegradable materials? Because it's just too much work and just not possible to go out and recover all of them once we've put them out into the field, out into the woods. So coming back to my ecological suppression model, I want to talk about some of my work that I've been doing now, which has actually been looking at plastics recycling with our synthetic polymers and commercial materials. And at a really high scale, one of the biggest issues that keeps us from being able to large scale recycle our materials is that we don't have great ways to sort them. So this is real time what a recycling kind of modern recycling infrastructure looks like with a picking robot. And this is a combination of optical and spectroscopic sensors that are saying that's a pop can, or that's polyethylene, that's PET. And it has a variety of vision that we're looking at these samples, but it's only so fast for the throughput that we need to do. And it's only so accurate, especially at the throughput that we're trying to give it. So there's still these kind of limiting features of where, how can we get sensors that can give us enough resolution of data and enough complexity of data that we can say, that's a pop bottle, it's PET, it's going over there. That's a pop lid, that's polypropylene, it's going in there. That's actually the body of a computer. It's black polycarbonate, and it's full of fire retardants and heavy metals because it doesn't go into the FDA process. And there's a lot of crap in there that we don't want in our kind of person contact recycling stream that's going to come back to us, putting us in contact with harmful materials that are already out in plastics. And so there's this big question of, how can we unlock these new modes of vision that allow us to faster and more efficiently separate our recycling? So I've been working with a technique called Raman spectroscopy. What's currently going through this structure is likely going to be near infrared spectroscopy, which is very fast, and it gives you these lumpy curves that a computer is very happy to deal with. But I look at one and I couldn't really tell you if it was PET or polypropylene. So Raman has a little bit more structural variation in our spectroscopy. Once you get good at pattern recognizing, you can say, oh yeah, that's a polyethylene, that's a PET. It's a little bit slower, but it has a lot of issues with interference. So like colorful plastics, or if it's been out in the woods for a bit and it started to get a biofilm or moss has started to grow on it, or it started to degrade in the sun, we'll get things like autofluorescence or fluorescence from the pigment. And then it's hit or miss if you're going to be able to identify it. But one of the things that we've been looking at with NIST is a special type of Raman spectroscopy called time-gated Raman spectroscopy. And what this does is we, instead of collecting a two-dimensional spectra, like is very common with Raman, we collect a three-dimensional surface and can unlock the time dimension. And what's useful with this is that the key to Raman is it's Raman scattering. And so this is a near instantaneous process. The delay has to do with how long is your fiber optic cable to get back to your detector. Fluorescence is an upconversion process. The incident laser light comes in, your molecule gets excited and scatters, goes to a high energy state, drops to a low energy state. You emit a photon of fluorescence, and that comes back. And there's a lot more of that from the Raman scattering. This is a fairly low probability event, whereas fluorescence is a very high probability event, and it floods your system, and then you don't get any signal. So what's useful with opening up that time dimension is we have about half a nanosecond where we kind of only have that instantaneous Raman scatter, and we can grab just the part of the spectra that we want and throw away all of this fluorescence that comes in and floods our system. And maybe it increases our chance of being able to see the spectra, fingerprint the material and say, okay, it's polyethylene. So this is some work that I did with an undergraduate student last summer. So we were looking at a bunch of ocean microplastics that were shipped out to us from a collaborator in Hawaii. And we were having a rainbow party. So my collaborator went out to the beach, and then it took her 5 different instruments to say, okay, yeah, that's red polyethylene. Plastics are really hard to identify once you start, especially if it's degraded, it's colorful. We're having a lot of issues there. And we also have form factors. So we have these kind of hard plastics that have degraded, very rough surfaces. Then we have fabric, we have fiber, we have old fishing line, we have fluff, thin films, you name it. So we've been using our Raman our special Raman instrument, as well as some correlation equations to try and up our throughput of being able to identify our polymers, even with kind of junky data. And even what's coming out of our Raman instrument is pretty junky. So this is what my undergraduate student Noel was able to find. And we found that, oh, that was not the right button. So red polymers, red dyes, very fluorescent. These were terrible to work with. Black also doesn't work very well. Blue is kind of okay, green okay. Clear, all day. We can do clear plastics. But I had another undergraduate researcher in the summer, and I had starting to get a better feel for the instrument, and we've unlocked that if you fry the sample with the laser for long enough, you can actually degrade the material that's fluorescing. So we can start to access the Raman spectra underneath with some more refined techniques, and also if we can route it through a microscope. And I apologize that I don't have any of that data because we've gone on shutdown and I can't access most of my data until yesterday. So the last piece that I want to talk about is the rest of my summer student Tyra's work, where we are looking at this time-gated Raman as actually a very much more powerful instrument than they market to you on paper. Because what we're happening is we're not excluding that fluorescence information. We're still getting it, but most people are just throwing this back half of the spectra away and saying, well, thanks, we don't want you. We can at least grab that front part and it's useful as Raman. But fluorescence spectroscopy is a whole field to itself. And there's a lot of useful information hidden in the fluorescence. It's maybe lower resolution. It's not going to tell us that like each one of these peaks is telling us that we have a carbon-carbon bond, we have a carbon-oxygen double bond. They have characteristic wiggles that are coming back to us as those peak information. But there's a lot of information in fluorescence. And so in principle, this orientation of the fluorescence spectroscopy should be pretty analogous to the emission profile collected on a UV-Vis instrument. And if we go to our other orientation, this in principle should be our fluorescence lifetime decay that you use another very expensive and quite rare instrument to collect what is our decay profile of these fluorescence photons. So what we have been working on this summer and into the kind of school year is trying to validate the time-gated Raman for extracting these fluorescence and lifetime profiles from our measurements. So it would be a 3-in-1 where we can get Raman spectroscopy, UV-Vis, emission profile, and fluorescence lifetimes all in one measurement that notionally takes less than 30 seconds. And so this is kind of one of our really exciting works because we've been working with well-characterized fluorophores, and we're very excited that we're getting pretty good alignment with our UV-Vis and lifetime imaging metrics. So we're hoping that maybe we can unlock this as a very dynamic instrument for analyzing plastics and autofluorescing types of materials of all types. So with that, I want to give some acknowledgements to my mentors, both in the PhD and in the postdoc, and my many collaborators. And I'd like to thank you for listening to me talk. Yes, thank you so much.
Questions, Rebecca and I?
Yes, please.
Thanks for that really interesting talk. And so I know that in the European Union, they have very few landfills, and they obviously produce a lot of plastic. And I assume that they incinerate.
It's incineration. It's a lot of waste energy.
Okay, and then do they do that in a way that is environmentally responsible?
Yes, to the best of our abilities. So when you burn plastic, there's a couple stages. Open burning, it's not hot enough to be complete combustion. So we're getting all sorts of larger molecules and pollution. And then to be like frank, you're kind of just concentrating the evil. So like whatever's in there, if you have a little bit of heavy metals in your general waste stream in a dilute state, when you reduce tons down to maybe kilograms, you're just, it's mostly inorganic material that's left. So you're really getting this kind of poisonous, highly concentrated heavy metals and ash carbon. And so in so much as possible, they're scrubbing anything that's off-gassing, maybe flaring methane or routing CO2 to alternative processes that use it. But there's still that question of, were you hot enough to destroy microplastics? Is there microplastics left in your ash? And what are you doing with that ash? Is it going to leach through the bottom somewhere, get into our water?
Okay.
Other questions? Julie?
Yes, please.
That was really nice presentation. Thank you for that. My question comes back to the different techniques that you're using now to identify plastics.
Yeah.
Have you considered, like, for example, doing one of these easier techniques like NIR or FDR, and then using like modeling, like principal component analysis modeling, and for instance, identify one specific peak that you see in polypropylenes and you don't see in polycarbonates, and then just basically a combination of this with the modelings and hopefully even in larger data set with AI to identify those plastics rather than going to more advanced methods that you're using?
Yeah, so that's a lot of my work is actually with principal component analysis and building up big data sets.
Mhm.
And I'm currently working with the NIST spectrometry data center. So we're going to kind of higher resolution technique with mass spectrometry and trying to build models of how can we actually use these higher resolution systems to inform my lower resolution Raman data. But I'm also working with my colleague is a machine learning scientist, and all of his work is in near IR and getting more complexity out of the near IR data. And we've been looking at kind of taking this cascade of complex data sets from the different instrumentations and merging them to try and get more and more out of our like lower resolution, really high throughput analysis techniques.
Yeah, that would be really interesting because NIR is the fastest ones and you
Certainly.
can get like with the small machines even in the collect the data.
Yeah.
Yeah.
You said this is in the beginning that this is a very interdisciplinary effort to connect engineers and waste managers and social scientists. Are there people or organizations that are like dedicated to doing this work since it falls under such a broad scope?
Yeah, it's a huge community of researchers. Like it goes all the way down to like a very adventurous kind of like running the local materials recovery facility all the way up to international discussions at the UN. Some of the most exciting work that I've been seeing is actually coming out of the Association of Plastics Recyclers. I believe they're an NGO or a nonprofit, and they're situated in North America roughly, and their huge thing is recyclable by design. So they're working on EPR schemes to go out and talk to Coke and Pepsi and Campbell's and say, if it's not recyclable, we're not giving you our certification. And there's moves to, like, California is currently working on making regulation that if your product doesn't follow the Association of Plastic Recyclers recyclable by design principles, that they won't be able to sell it in California and maybe even the EU. And there's a lot of work at a lot of different kind of frames of what plastic pollution means. Yeah.
For interviewing farmers, there were the same people who were recycling and burning. Was there like a particular material that people would burn instead of recycle? Like was there a clear about what people were?
Yeah. Let's see. Can I? Oh, I really escaped it. Share. Back up to. So this is films on the rigid plastic. And so our recycling is these little green bars at the end there versus the red bars, which are burning. And there's very low access to recycling programs and what kind of value we're getting out of these materials when you primarily mechanical recycling, so melt it down and re-extrude it into pellets and then re-extrude it into something that you can use. These are mostly dirt by mass, like upwards of 50% to 60% dirt by mass when you're carting it in. It's not a very good value proposition to anyone on the stream of where value could be produced and something that you're trying to market as a business. So it's a very difficult solution because like we can collect it and there's a little bit of will to collect it, and the farmers really want something. They want to be able to collect it and recycle it, but it's just the money isn't there. Yeah, they're doing a lot better in Europe. So this paper, it says 2026 in the future, but that's live now. And hidden in the SI, I've done a literature review of probably about 40 countries recycling programs for agricultural waste, if you're interested in seeing a little bit more about what's there. And like the EU countries, Canada, Japan, Korea, they have they're moving towards more robust agricultural recycling capture. And a lot of that's motivated by like legislation and policy that say, you plastic producers have to fund our programs, and you people over there, you have to cooperate, or we're going to give you a fine if you're. So there's the incentives are moving more into a place to get people to buy in. Yeah, let's see back there.
Do you think the scale has maybe also to do with the EU having like less, or like doing better recycling like in agriculture, because like most farms in the EU are like much smaller compared to operations in the US, and I could just see that a farmer who was like, I don't know, plastic from 100 people to 1,000 people, like
Yeah, it's such a complicated comparison, because it's like it's your political structure, it's your economic structure, it's your culture of like, do we like our government? Like, are people going to cooperate with you? Because like at the time that I went down there, I had to be under the banner of the federal government and say, I'm from the government, I'm here to help, talk to me. And like a lot of people didn't want to talk to me. It was very hard to draw people in and actually do my survey. And so there's a lot of identity politics too, of when you go out into these communities, and like, what are you going to learn from them, and how are they going to perceive you and what you're trying to do? And from all of those angles, there's complexity.
I have a question.
Yes.
So you show that the production of the plastic just goes like exponentially over time.
Yeah.
And that's figure like scare the heck out of me. And is it going to be like increase over the time? Like,
So let's play a game. So mentally, you're an oil baron in Saudi Arabia, and your country's entire GDP is petroleum. And oh my gosh, these electric cars are a big deal. They're outlawing gas vehicles. All of my money comes from petroleum. We're going to do something with that. And so that kind of downward pressure on fuel and oil cars is being squeezed into plastic production. So you get that same kind of reinforcing feature of, we flood the market with virgin plastic, the price comes down. Recycling is still technologically difficult and expensive, and it's a worse product. And now it's more expensive than the virgin plastic. And why? That's where consumer demand comes in. So the companies are getting these calls, and the people are saying, we want recycled materials in our plastics. And so the companies are like, okay, we'll use a little recycled material. But there's still like, there's political play, and what does it mean to be some quantum of recycled material? And it's complicated and fuzzy and political. And so there's this, the geopolitics really comes into play too, of where is the money flowing, and who can afford to stop producing plastic or give up plastic.
thank you so much.
Yeah, thank you.